Hey guys, my name is Hiraku Murakami, back with NovaEdge Academics. Today we continue with topic C5, Doppler Effect. Now this topic is actually one of the shortest and it's actually one of the easiest too. So once you understand it, I hope you'll ace your exam. So let's just dive right in. So what is Doppler Effect? Well, Doppler Effect is a phenomenon where frequency of wave is perceived differently due to movement. Okay? Now I want you to picture an ambulance coming at you, right? Maybe you've noticed on the street, if you're standing on the street and an ambulance passes by you, you go beep boo, right? That sound, the moment it passes you, frequency or the pitch drops significantly. So it goes beep boo, beep boo, beep boo, beep boo, beep. Like it goes down. Okay? I'm not able to recreate the sound perfectly, but maybe you've noticed that. Now, this is not something about volume, okay? This is not about amplitude of the wave. It is about the frequency of the wave. So it goes from beep, boop, beep, boop, beep, boop, beep. Like it drops the moment it passes you and it's going away, okay? Of course, volume increases and it goes down, right? But that's not something that's about Doppler effect. Doppler effect is about the pitch, okay? And this is due to physics. So I'm going to explain that physics to you. So imagine the ambulance is coming at you. What's going on? They're emitting sound, right? So first, if the ambulance was stationary and it was emitting sound, at t equals 0, it emits the first wave, right? And then at t equals 2, what happens? Well, this wave travels farther, and then the second one is emitted. At t equals 3, what happens? Same thing. This wave travels further, this wavefront travels further, and a new one begins, right? And when this hits you, when this continues to expand, I'm not going to expand it, when this expands, pretend it's expanding towards you, what you perceive as the pitch is due to this wavelength. This is wavelength, right? We know the distance between two wavefronts, like we did in here. Two wavefronts is the wavelength. And subsequently, of course, you have velocity of sound at around 330 meters per second. And so therefore frequency is v over lambda, right? So this pitch that we're hearing is due to the sound wave and the frequency of the sound wave, right? What happens if the ambulance is traveling towards you? So if I had the ambulance, and let's say this was the ambulance, okay? First it emits the first wave. At t equals 0, it emits the first wave. But then the ambulance is moving, right? So at t equals 2, this guy is expanding, and a new wave centering this guy is issued, right? T equals 3, same thing. This guy keeps expanding. This guy also expands. And then a new wave at its new position emits another sound wave, right? So I want you to see that if I'm standing on this side, what's happening is these wavefronts are being squished together, right? I can continue this. How about t equals 4? I expand it further. These guys are traveling, and then this guy also moves and creates another sound wave, right? Boom, right? So what's happening is these wavefronts are being squished, which means that the wavelength is now less. Wavelength decreased, meaning frequency increased, which means that if the ambulance is traveling at you, right, then that means you perceive the sound to be at a higher frequency than the actual sound being emitted. Okay, so if I make the frequency perceived to be this frequency apostrophe, it is greater than the frequency that's being emitted. Now, same thing. Once the sound crosses, what happens? Well, now this wavefront distance increases. So the moment it passes you and it's going away from you, the pitch decreases. The frequency goes down significantly. Okay? And that's why we have this whole thing of Doppler effect, where hopefully you've noticed in real life, the moment the ambulance passes you, the sound pitch decreases. Okay? But what about, let's say, if the ambulance wasn't moving, but then I am moving towards the ambulance? What happens? Well, I'm going to get a wave front like this, right? The same thing. It's emitting sound at a specific frequency, right? So this is the wave front. But if I'm the one moving towards it, from what I experience, the wave fronts, they seem like they are shrinking. Because let's say it's me right here, right? Let's say I am traveling at the ambulance. What's going on? Well, this is a distance to cover, but then I'm going towards it. So I'm actually experiencing that the length is shorter. So I'm experiencing that the wave lengths are shorter, which means, again, frequency increases. Same thing, if I was moving away from the ambulance, frequency decreases. So that's the whole point of Doppler effect, where the frequency of wave that's perceived is different from the frequency of wave that's being emitted. Okay? Now, before I dive into Doppler calculation, I just want to note that this is an HO section. However, if you're an SO, you have a section of topic 5.3 later, and well, you're gonna need to watch that part, right? But it's also important to know the HO concept as well, because Doppler calculation, a lot of the times the concept just doesn't register right until you do practice problems and calculations. So if you're interested in really learning about Doppler effect, then I suggest you to continue watching the HO part and do the HO content together. Okay? Now, what is the math behind it? Because there is definitely a math behind it. We use two equations, this guy, and it's in your data booklet. It's important to know which one to use because you need to understand the scenario. If you have a moving source like an ambulance moving towards you, you need to use this equation. If you have a moving observer, you need to use this equation. Now, how do you remember this? Well, they write it in the data booklet, but also they tell you US and U0, UO. US is the velocity of source, the speed of ambulance. U0 or UO is the speed of the observer going at the person. Now, why is it plus minus? Well, that's because it depends on whether the moving source is coming at you or going away from you. You'll have to always remember conceptually that frequency increases if it's moving towards you or if you're moving towards it. Anything that's moving towards each other, the frequency increases. Okay, so you need to see which one is applicable. For example, if the ambulance is going towards a guy, I know this is minus because if the denominator is smaller, then this becomes bigger. Okay, therefore frequency perceived becomes bigger. But if I do the opposite, then frequency becomes smaller. So that's when the ambulance is going away from you. Okay, now rather than me just yapping about this, let me just do a practice problem so you can get used to it. So pause the video and give this one a try. Okay, so we have a moving source, a source of sound emitting frequency of this is moving directly towards a stationary observer at 50 meters per second. So in this case, we use the moving source. The source is moving towards the observer. So frequency is equal to Now, why do I know it's minus? Because by doing minus, the denominator goes down and this whole thing goes up. So I know frequency prime has to be greater than the normal frequency. Okay, now if this was going away, directly going away from the stationary, then this will be plus and it will be a different calculation. Okay, part B, what frequency would be heard on a cold day when the speed of sound was 330? They just want us to change V. Okay, part C, explain why the speed of sound is less on a colder day. Well, conceptually speaking, how does sound propagate? It propagates through air molecules. Now, in a colder time or colder day, the air molecules move slower. That's the whole point of temperature, right? It's the average kinetic energy. It's how fast or slow they're moving. So that's why the speed of sound is less on a colder day, okay? Now, one thing that's really important about application of Doppler calculation or Doppler effect in general is radar. Okay, these speedometers that's being used to measure the speed of a car. How does that work? How do we measure a speed of a car in a distance? Well, we have an instrument that sends a frequency like a ultrasound. Okay, it sends a wave and it hits the car, right? And that car actually bounces it back. And we can calculate using Doppler effect what speed this car was traveling at based off of the frequency that we received back. Okay, now one thing that's really important, right? This is really fascinating, right? It's a fascinating concept, but one thing that's really important about this is there is two things that are going on. The first scenario is the police officer sending the wave to the car. Okay, now the car is going to perceive this, right? Because the car is the observer it is the one that's moving, so it uses the second equation. In fact, this is not plus minus, it's just plus, right? Because we know frequency has to be greater if it's moving towards each other. Okay? But here's the second thing. Now the car is actually bouncing it back. Okay? So when it bounces back, it now acts as a source. So in the second part, it's acting as a source. And now the police officer is the observer. So now it's sending this wave, right? But then the one that the police officer is perceiving, f prime prime, which is, this is actually minus. We use the first equation. Why? Because now the car is acting as a source. It is the moving source. And the police officer is receiving that moving source as a stationary observer. So now we use the first equation. Well, let me put this from perspective, because the police officer, it knows the frequency it sent, which is f. It knows the frequency it sent, and it can measure the frequency prime prime, which is what it's receiving. And we want to get the velocity now, okay? So we know f prime is equal to this. So it becomes like that, okay? And we know we can cancel out mathematically these two. So it becomes basically f prime prime is equal to and by the way, u0 and us are the same thing because it's the speed of the car. Now, why am I talking about this in such a deep depth? Because they will ask you in your paper 2 exam a similar question where you need to be applying Doppler effect twice. It's not just once, it's twice, so it becomes a bit more complicated. So you need to know when to apply twice and when to apply only once. You need to apply twice in a scenario where you have bouncing back and coming back, like this exact scenario, okay? Let's do a practice problem, and you need to be able to derive it on the spot like I just did right now. Okay, so let's do a practice problem. Now pause the video and give this one a try. So we know this is similar to the previous slide where you have a police officer or a source sending 30 kilohertz, and you have a car that's receiving it, and it's going to receive this, right? And then it's going to send it back because it's bouncing off of it. So now it sends it back at f prime. And then this guy is going to receive it at f prime prime, which is equal to f prime, this, right? If you're not sure why, then look at the previous slide and the previous section, then you'll figure it out. What needs to happen now is we need to mathematically correlate between the frequency that was sent and the frequency that was received, because this we know it to be 32.7. Right, so how do we do that? Well, we use this correlation. Okay, and lastly, it simplifies down to basically, because we can cancel this out. Right, perfect so far. Let me erase this because we have no space. All right, so we got to here. We know f prime prime, we know f, we know v, but we don't know us or u0. Now, by the way, us is equal to uo because that is the speed that the car is traveling at. It's the same thing, right? So let me just replace it by u. Okay, and now we need to isolate u to figure out the speed of the car. Pretty tricky, right? So first to deconstruct this and rearrange it. Multiply both sides by v minus u. Let me bring this here. Factor out v and u. And isolate u. And solve. So plug in those factors. V is equal to 335, f is 30, and f prime prime is 32.7, and you get 14.4 meters per second. Okay, hopefully that sounds about right. If I change that to per hour, meters per hour, that's about 51 kilometers per hour, 52 kilometers per hour, which sounds about right. So I'm gonna trust my calculation on that one. Okay, hopefully you got the same thing, and if I did make any mistake on this, then leave it down below. Okay. Now, one thing that's really interesting about this whole Doppler thing is visualizing how it looks like with sound waves, right? How it's being propagated. One thing that's really interesting that I thought I would bring up is about supersonic planes. Now, Mach 1 is the speed at which you're traveling at the same speed as the sound. If you go beyond the speed of sound, we call it supersonic. And maybe you know that a lot of the military planes can travel at greater than the speed of sound. And this is the effect that happens. It kind of creates this sound barrier, and it's really, really cool. Now, one thing to visualize in Doppler's effect is visualizing how you perceive the sound, right? Now, can you imagine if you were next to the supersonic plane, what kind of sound you hear, or when do you hear the sound? In fact, you hear the sound after the plane passes you. So it's a really interesting concept, and I think I'm just going to show you a video of it. It's a really cool video, right? So the thing that I want to highlight is the fact that the sound wave doesn't get to you until the plane is right next to you, because this is the position of the plane. So all of these sound waves that was emitted before, they haven't reached you yet because the plane is traveling faster than the speed of sound. Okay, pretty cool thing. Now, if you are interested in engineering concepts, then I highly recommend you watching this video by Real Engineering on supersonic planes. It's really interesting how they designed this plane's wings and stuff like that. So, you know, as you're finishing up your second year, what you're trying to determine is what kind of studies you want to do, right? And so if you're interested in engineering, because I study engineering and I am an engineer, then I would highly recommend watching video of this. I will link it down below, okay? Last thing I want to talk about is the Doppler effect for EM waves. So I said Doppler effect is just about waves, right? So of course you can have Doppler effect for electromagnetic wave. In fact, this is something that's being used to study space, what's going on in space. So now this is a perfect example where you have a telescope pointing outside towards a space, right? Now, if there's another solar system, like a neighboring solar system, and there's a planet orbiting another sun, right? What you measure and you receive the frequency back is different from what you send it, because the planet might be traveling towards you or away from you. Now, the one that's coming towards you, the wavelength will be shorter and the frequency will be bigger. You see it here, right? Wavelength is shorter. Wavelength is shorter. But then if it's the one that's going away, then you have wavelength that's bigger. So we actually call this blue shifted and red shifted. This is actually really important. Okay, this is due to Doppler effect. Another thing that's due to Doppler effect is the measurement of elements. We know like gaseous elements, they can absorb certain frequency and then release it back, right? And we create this absorption spectrum like a fingerprint on elements, right? So let's say if I do it towards a hydrogen gas at the neighboring planet, what happens? Well, we actually see a little bit of a shift called a redshift. And the reason why is because the planet is shifting away from us. So this is actually one of the reasons why we know the universe is expanding, because when we measure these elements from different planets, they are all going away from us. Now, one misconception is, does that mean we're at the center of the universe? This is not. We could be one of many stars or one of many planets, celestial bodies. Maybe this is the center. Maybe this is us, right? But they're just moving faster than us. So, and the ones that are behind us, essentially these guys, are moving slower than us. So they're still going to be redshifted. So everything around us is redshifted. So we know that everything is expanding. We are not the center of the universe, but everything is expanding from the center and onwards. Okay? Now, what about quantification in mathematics? This is something you need to know for SL as well. Well, we have the same kind of frequency calculation that we can do, except it will take into account relativity. So it's actually derived from relativity. It looks similar to what we've covered before. By the way, this takes into account when you send a wave and it's reflected back. Like it's the same way that the police speed radar works. It takes account both of them, okay? We use this equation, which is a much simplified one. If you want the derivation, I could show you the derivation. In fact, okay, I'll just do it quickly. This part is equal to 1 plus v over c. So delta f is just this, because this is this, right? So it goes towards here. This is a derivation from that, and that's where you see it here. Okay, now this derivation, of course, you don't need to know. I just thought I would show it quickly. This is what we use for EM waves. So anything that's EM waves, you use this guy. Okay, so let's do a practice problem to end this video. So pause the video and give this one a try. Okay, so we're given delta lambda. This is the answer, or 2.16 times 10 to the power of 7 meters per second. Okay, so this is how we can calculate how fast a neighboring planet or a system is moving away from us. Let's do another one, pause the video, and give this one a try. Okay, so we know the velocity and speed of light, so okay, so that's the answer. I hope you got the same thing. Okay, so that concludes topic C in general, so we'll see you in the next one in topic D.
Hey guys, thanks for watching. If you like this kind of video, then consider giving us a like and subscribing to our channel. We have a lot more lecture style video and content like this in our channel, so feel free to go check it out. If you're looking for additional guidances like one-on-one tutors in IB subjects, SAT, TOK essay, IAs, writing, etc., then go to our website at NovaEdgeAcademics.com, fill out the form, and get in touch with us. In the meantime, we'll see you in the next video.